Let's jump right into it. Welcome to the Explainer. If you really want to know what's going on under the hood, well, actually, scratch that. It's more like under the floorboards of modern electric vehicles. You are in the exact right place. Today, we're zooming in on the mechanical heart of the EV. We're going way past just the battery and looking right at the true engines of this electric revolution. Yep, we're talking about the motors and the powertrains. And to kick things off, I've got a question that might sound a little bit out there at first. Does an electric car actually just need one motor, or could it use four? Because as you're going to see, the number of motors you pack into these vehicles, it completely rewrites not just the raw power, but the fundamental agility of the car itself. So here's our roadmap for today. First, how EV motors actually work. Second, we'll compare 7 different motor types. Third, we'll look at single versus dual motor setups. And finally, we'll cap it off with 3 and 4 motor power. Okay, let's dive straight into section 1, how EV motors work, the basics. So if we strip away all the ultra-complex engineering for a second, an electric motor really just relies on 2 main players, the stator and the rotor. The stator is the fixed, completely stationary part of the whole setup. You pump an electrical current into it, and boom, it creates a magnetic field. Then, right inside or alongside that stator, you have the rotor, which is the part that actually, rotates. Honestly, it's kind of like a high-speed game of magnetic tag. The stator generates this rotating magnetic field, and the rotor is just constantly chasing it, spinning like crazy as it tries to catch up. Let's walk through exactly how this plays out in a standard AC induction motor. Step 1. The car's battery shoots electrical energy straight to the stator. Step 2, the stator coils, which are set up on opposite sides to act just like magnets, create these incredibly powerful rotating magnetic fields. Step 3, conducting rods sitting on the outside of the rotor get physically dragged along by those magnetic fields, which makes the rotor spin. And finally, step 4, that spinning rotor churns out the mechanical energy needed to turn the car's gears, pushing the tires forward. It is literally just this beautiful, elegant transformation of raw electrical energy into pure physical motion. Moving right along to section 2, comparing 7 motor types. Now, if you want to understand why EVs are such a massive game changer, just look at this number, 95 to 98%. That is the operating efficiency of a brushless DC motor, which is one of the heavy hitters in the EV industry. Think about that for a second. That means there is virtually zero wasted energy. It sets this insanely high baseline of excellence that those old, heat-spewing gas combustion engines absolutely cannot touch. Now, what's really fascinating is how these abstract engineering concepts actually hit the pavement in the cars we see every single day. Let's look at 4 major contenders. First, the brushless DC motor, like you'd find in a Toyota Prius. It's virtually maintenance-free and highly efficient, though it can be a bit costly and has a shorter constant power range. Next up, the permanent magnet synchronous motor, or PMSM. Cars like the BMW i3 and Chevy Bolt use this because it offers an amazingly compact, high-power density design, even if it trades off some huge iron losses at high speeds. Then we have the induction motor. This one is cheap to make, but delivers staggering high performance. It's the go-to for performance EVs like the Tesla Model S, though it does require a pretty complex inverter circuit to run the show. And finally, the axial flux motor. This thing is totally slotless, ironless, and ridiculously lightweight because it completely ditches the stator core. It's cutting-edge tech that you'll see in beasts like the Renault Coupe. To round out our list of 7, we have a few more niche or even obsolete categories. The switched reluctance motor is super robust and handles high speeds beautifully, but it definitely struggles with noise issues and tricky controls. Then there's the synchronous reluctance motor, which is getting really popular lately. Why? Because it completely eliminates rotor cage losses and hands you massive permanent torque. And finally, the brushed DC motor. Sure, it gives you high torque at low speeds, but the brushes generate a ton of heat right in the center of the rotor, which is a total nightmare to cool down. Because it's so bulky and inefficient, the brushed DC motor has basically been left in the dust. It's totally obsolete in modern EVs. All right, zooming out a bit, let's hit section 3, single and dual motor setups. When it comes to powertrains, you're basically looking at 2 main philosophies: centralized single motor drives or distributed multi-motor drives. A single motor setup is beautifully simple. It usually drives just the front wheels, needs far fewer components, uses an adapted conventional transmission, and is of course way cheaper to build. But then you have the dual motor setup. This is where you drop a motor on 2 different axles and suddenly you've got yourself a complex, high-performance, all-wheel drive machine. Let's anchor this in the real world with the Polestar 2 and the Tesla Model 3. The Polestar 2 offers a single-motor front-wheel drive version. It's easier on the wallet, and honestly, it feels a bit more like driving a traditional gas-powered car. That's fantastic for first-time EV buyers, though it maxes out at around 160 kilometers per hour. Contrast that entirely with the dual-motor Tesla Model 3. With two totally independent motors digitally managing the torque going to the front and rear, this thing screams to top speeds of 260 kilometers per hour, all while maintaining a massive 576-kilometer range. So the crucial point here is that adding a dual-motor setup isn't just slapping more parts into a chassis for the fun of it. It fundamentally upgrades what the vehicle can do. We're talking a massive boost in acceleration and horsepower. It easily outperforms single motors at higher altitudes, too. But the real magic? It's incredibly smart. It actively distributes horsepower based on immediate road conditions. It can even use one motor to drive the car while the second motor purely regenerates the battery through braking. Plus, having that independent drive on the front and rear axles unlocks torque vectoring, which drastically enhances your traction and stability. It's a total game changer. Which brings us to our final stop, Section 4, 3 and 4 motor power. Let's see what happens when engineers get really crazy. In a 3-motor setup, which you'll find in ultra-high-end models like the Audi e-tron S or the Tesla Model S Plaid, engineers put one motor on the front axle and two entirely independent motors on the rear axle. Here's how it works. During a normal, everyday drive, those two rear motors do all the heavy lifting to maximize efficiency. But the second you need raw power, that front motor wakes right up. But here is the absolute best part. Because each rear wheel gets its own dedicated motor connected via a single-speed transmission, it completely eliminates the need for a heavy traditional mechanical differential. That is a huge leap forward in automotive engineering. And this brilliantly illustrates how this tech totally transforms the driving experience. By focusing the driving feel on the rear and digitally micromanaging exactly how much power gets sent to the left or right rear wheel, this powertrain feels incredibly sporty. Like the source material points out, powertrains like this are very eager to drift. It literally gives the driver a level of handling, stability, and grip that mechanical systems just simply cannot replicate. Now, let's take this to the absolute extreme, the 4-motor setup. This system dedicates a completely individual electric motor to every single wheel on the car. Because everything is electronically adjusted, the computer can apply incredibly precise positive or negative torque to each individual wheel in real time. Imagine you're taking a super tight corner. Normally, your inside and outside wheels want to rotate at the same rate, but with a 4-motor setup using proper torque vectoring, the car can apply aggressive power specifically to the outside wheel, physically pushing the vehicle into a sharper, tighter turn. It maximizes vehicle agility in a way that honestly feels a little unnatural if you're used to the old mechanical limits. Let's see how this actually builds into the physical architecture of the car itself. Currently, vehicles with 4 motors, like the Rivian R1T, use an inboard setup. That means the motors are tucked securely inside the vehicle's chassis and use shafts to connect out to the wheels. But then there's the future, in-wheel or hub motors. Imagine if the majority of the motor was actually contained entirely within the physical wheel itself. By pushing all of that hardware out to the extreme periphery of the car, you free up massive amounts of space right in the body of the vehicle. More room for cargo, bigger batteries, extra passenger space, you name it. It makes the entire design incredibly efficient. Which brings us to the end of our explainer today, and it leaves us with one massive, lingering question to think about. Which EV powertrain setup is the true future of driving? Will the cost-effective, perfectly simple single motor stay the standard for the everyday commute? Or will the unparalleled agility and brilliant space-saving design of the 4-motor in-wheel setup eventually become the blueprint for every single car on the road? Honestly, it's something to think about the very next time you see an electric vehicle silently accelerate past you. Thank you so much for joining me for this deep dive into EV motors, and keep learning.